The James Webb Space Telescope has just challenged traditional cosmological models about the scale and the process of formation of the universe. By observing infrared light emitted from the very early epochs of the universe, scientists have realized that the observable universe has a scale of up to approximately 93 billion light-years and may contain trillions of galaxies far exceeding previous estimates. More importantly, Webb has revealed a series of paradoxes, primordial galaxies, and supermassive black holes appearing too early, too large and too evolved compared to the theoretical timeline after the Big Bang. These observations portray the universe as a light archive, where the expansion of space makes the observable universe larger than its actual age, and every astronomical image is essentially a memory of the past. Webb has pushed that memory deep into the era of cosmic birth, revealing a formation process that is faster and more violent than expected early galaxy growth, possible traces of population 3 stars, and a dark matter network that shaped the structure of the universe from a very early stage. At the same time, data on redshift voids and especially the Hubble tension show that the expansion rate is not consistent across different epochs. All of this suggests that the current standard cosmological model may be incomplete, and that the early universe was far more complex and accelerated than previously imagined. Do these new discoveries from James Webb rewrite the history of science as we have long known it? We will explore this together right after this. For most of human history, distance felt intuitive. A horizon was something you could walk toward. A star was something far away but still anchored to a sky that felt finite. Even when astronomy taught us that the universe began nearly 14 billion years ago, the number felt complete, almost comforting, as if time itself had drawn a clean boundary. But that comfort quietly dissolves when we ask a deeper question. If the universe is about 13.8 billion years old, how can its observable size stretch to nearly 93 billion light-years across? The doubt does not come from speculation. It comes from light itself. Light does not travel through a static stage. It moves through space that expands while the light is in motion. A photon leaving a distant galaxy begins its journey when the universe is young and compact. As it travels, the space between every point slowly stretches. Not because the photon slows down, but because the fabric it crosses grows longer beneath it. This is why the most distant galaxies we observe today are no longer where they once were. They have been carried away by expansion for billions of years, drifting far beyond the place where their light began. The result is a universe that appears vastly larger than the time available for light to cross it. Imagine painting 2 dots on the surface of a balloon. As the balloon inflates, the dots move apart even though neither dot is travelling across the surface. Space behaves the same way. Galaxies are not racing through space. Space itself is quietly, steadily widening. This realization reshapes our sense of scale. The observable universe is not a sphere carved out by light speed alone. It is a growing window defined by what light has managed to reach us while the window itself expands. Beyond that window, space continues. Galaxies exist there. Light shines there, but their signals can never arrive. Here, the doubt deepens. If our cosmic map only shows what expansion allows us to see, then our picture of the universe is not a full portrait. It is a fragment stretched thin across time. And as we begin this journey, it's worth holding that thought gently. What we call the universe may be only the part that managed to speak to us before silence set in. Every image captured by a telescope is already old. Even the light from the moon reaches Earth a little late, carrying a delay of a few quiet seconds. Starlight arrives years behind its source. Distant galaxies send us messages that have been travelling for billions of years. In astronomy, seeing is never happening now. Seeing is always remembering. This is why light can be thought of as a fossil. A fossil does not show an organism as it once moved or breathed. It preserves a moment frozen in structure long after the living process has ended. In the same way, every photon collected by a telescope preserves a precise instant from the past. When that photon began its journey, the universe was younger, smaller, and fundamentally different from the one we inhabit today. As light travels, it does not simply cross empty space. It carries with it information about the conditions under which it was born. Its colour, its energy, its subtle patterns are shaped by temperature, motion, and chemical composition at the moment of emission. When that light finally reaches our instruments, it brings a record of ancient environments that no longer exist. The James Webb Space Telescope was designed to read these records with extraordinary sensitivity. Its detectors gather faint infrared photons that have been stretched by cosmic expansion, photons whose original visible or ultraviolet wavelengths have been elongated across billions of years. Each stretched wavelength is a clue, a timestamp embedded in light itself. By dispersing this light into spectra, scientists can decode its history. Tiny gaps and lines reveal which atoms were present. Shifts toward the red reveal how much the universe has expanded since the light was released. Together, these measurements allow astronomers to place each photon within a precise moment of cosmic time. Yet there is something quietly humbling about this process. Webb does not show us the universe as it is. It shows us layers of the universe as it was stacked across time like sedimentary rock. The deeper we look, the older the layer becomes. We are not observing motion, we are excavating memory. In this sense, the night sky is not a window, it is an archive. And as we move deeper into that archive, reading older and older fossils of light, we begin to realize that the universe's earliest chapters were not silent or simple. They were already rich with structure, activity, and unresolved questions waiting patiently for their light to arrive. There are moments in science when an observation does not feel surprising but unsettling, not because it is dramatic, but because it appears too complete for the time in which it exists. JD's JUS 14-0 is one of those moments. This galaxy reveals itself at a distance so extreme that its light began travelling when the universe was only about 290 million years old. In cosmic terms, this is infancy. According to long-standing models, this era should have been quiet. Stars were expected to flicker into existence, cautiously assembling into small, dim collections, barely holding themselves together. But JD's JUS 14-0 does not behave like a hesitant beginning. It appears bright, structured, already mature enough to challenge expectation. Its size, while modest by modern standards, is unexpectedly large for its age. Its stellar mass suggests hundreds of millions of suns burning within it. The light it emits is not the weak glow of a newborn system, but the confident radiance of something that has already settled into rhythm. This creates a tension that cannot be ignored. Gravity is patient. Gas collapses slowly. Stars require time to ignite, evolve, and influence their surroundings. Every step in galaxy formation carries a built-in delay. Yet here is a galaxy that seems to have crossed those steps far too quickly. Even more troubling is what its light contains. Spectral analysis reveals not only hydrogen and helium, the simplest elements formed after the Big Bang, but heavier atoms as well, carbon, oxygen, elements forged inside earlier generations of stars. Their presence implies that other stars lived and died before this galaxy took shape, compressing an entire cycle of stellar evolution into a window that appears uncomfortably narrow. Scientists did not accept this easily. The data were questioned, the brightness remeasured, the distance recalculated. Instruments were checked, then checked again, but the signal remained. JD's JUS 14-0 persisted quietly, insisting on its reality. It does not announce a new theory. It does not explain itself. It simply exists, occupying a place in time where, according to expectation, it should not. In the stillness of deep observation, this galaxy becomes more than a point of light. It becomes a question suspended across billions of years, a reminder that the early universe may not have unfolded cautiously, but with surprising urgency. And if one such galaxy exists at this distance, it invites a softer, more unsettling thought. Perhaps it is not alone. The presence of a single unexpected galaxy might be dismissed as an outlier, a rare fluctuation, a statistical curiosity. But the deeper James Webb looked, the harder that explanation became to sustain. JD's JUS 14-0 was not alone. It was part of a pattern. In regions of space where models predicted scarcity, Webb found abundance. Not a handful of early galaxies, but dozens. Not dim, fragile systems, but luminous ones. When astronomers compared these observations to theoretical predictions, the discrepancy was not subtle. The early universe contained nearly 10 times more galaxies than expected. This points toward a deeper question, one that shifts the focus from individual objects to process. How efficiently did the early universe turn gas into stars? In modern galaxies, star formation is remarkably inefficient. Vast clouds of gas drift for millions of years, collapsing slowly, resisting gravity through internal pressure and turbulence. Only a small fraction of available material ever becomes stars. The rest is heated scattered or blown away by stellar winds and radiation. This inefficiency is not a flaw, it is a balance shaped by physics, but the early universe appears to have played by different rules. The density of matter was higher, galaxies were closer together, gas flowed along cosmic filaments more readily feeding young systems with fresh material. Under these conditions, gravity may have worked with unusual intensity, compressing gas faster and more uniformly than it does today. Collisions between gas clouds were more frequent, triggering rapid collapse and ignition. Observations support this picture. The brightness of early galaxies implies star formation rates far exceeding those of comparable systems in the present universe. Some appear to have converted their gas into stars at rates 10 to 100 times higher than what we observe locally. This is not a small adjustment, it is a fundamental shift in efficiency. Yet this raises a paradox of its own. If stars formed so rapidly, why did these galaxies not burn through their fuel almost instantly? Sustained star formation requires a continuous supply of gas. One possibility is that cold streams from intergalactic space fed these galaxies, steadily replenishing what was consumed. Another is that feedback mechanisms which regulate star formation today had not yet fully developed. There is also the possibility that the stars themselves were different. If the earliest stellar populations were biased toward massive stars, they would shine far brighter for the same amount of material. A galaxy could appear mature without containing as much mass as its light suggests. None of these explanations stands alone. Each offers a partial answer, but none fully resolves the tension. What remains clear is that the early universe was not cautious. It was productive, urgent, almost impatient. Stars did not wait politely for conditions to settle. They formed quickly in large numbers, rewriting the expected pace of cosmic history. And as we will soon see, this urgency did not stop with stars. If early galaxies formed stars with surprising urgency, their centers reveal an even deeper puzzle. Hidden within several of these ancient systems are objects whose existence seems to compress time itself, supermassive black holes. Black holes are not born large. In the modern universe, they emerge from the collapse of massive stars, leaving behind remnants only a few dozen times the mass of our Sun. From there, growth is slow. Matter spirals inward, heating, glowing, and often pushing back against further infall. Physics sets a limit on how fast this feeding can occur, and yet Webb has identified black holes in the early universe, weighing millions, sometimes billions of solar masses, when cosmic time had barely begun. At an age of just a few 100 million years, the universe should not have had enough time to build such giants through gradual growth. Even under ideal conditions, steady accretion would fall short. The math refuses to cooperate. This has led researchers to consider more abrupt beginnings. One possibility is direct collapse. Instead of forming stars first, enormous clouds of pristine gas may have collapsed all at once, bypassing stellar stages entirely. In this scenario, a black hole could be born already massive, skipping millions of years of slow assembly. Another idea involves the remnants of the first most extreme stars. If those early stars were far larger than anything we see today, their deaths could have seeded unusually heavy black holes, giving growth a head start. Mergers may have also played a role, as dense early environments allowed black holes to collide and combine more frequently. None of these paths is fully confirmed. Each remains a hypothesis carefully tested against observation and simulation. What is certain is that these black holes were not passive. Surrounding gas shows signs of intense accretion, glowing as matter falls inward at remarkable rates. These objects were already active, shaping their galaxies almost from the beginning. In the quiet darkness of the early universe, gravity did not wait. It gathered, collapsed, and deepened faster than expected. The presence of these black holes suggests that cosmic structure may have formed not step by step, but in bold leaps. And to understand those leaps, we must look even further back to the stars that may have come before all others. Before familiar stars filled galaxies with steady light, the universe may have hosted something far more extreme. Population 3. Stars are not observed directly, yet their fingerprints appear quietly in the data embedded in ancient light, like a memory that refuses to fade. These stars are thought to have formed from pristine gas composed almost entirely of hydrogen and helium. No heavy elements existed to help regulate collapse. Without those stabilizing ingredients, gravity may have driven gas clouds to grow larger, hotter, and more massive than anything that forms today. In this environment, stars could have reached sizes thousands of times greater than our Sun. Such stars would have lived fast and brief lives. Their immense mass would force nuclear reactions to proceed at furious speed, flooding their surroundings with intense radiation. They would burn brilliantly, then vanish within a few million years, collapsing directly into black holes without the familiar explosion of a supernova. Evidence for their existence does not come from images, but from chemistry. In some of the earliest galaxies observed by Webb astronomers, detect unusual ratios of elements, particularly nitrogen, that cannot be produced easily by normal stellar populations. These ratios match theoretical predictions for the interiors of massive primordial stars where exotic fusion cycles dominate. If population 3 stars did exist, their role would have been profound. They would explain how heavy elements appeared so early. They would offer a natural pathway to forming massive black hole seeds, and their radiation would have helped transform the universe from an opaque fog into a transparent luminous space. Yet these stars remain hypothetical. No telescope has seen one directly. They are inferred, reconstructed, and modelled, existing at the edge between evidence and imagination. In the stillness of cosmic dawn, these stellar giants may have risen briefly, altered everything, and disappeared without leaving a visible trace, except for the quiet chemical echoes we're only now learning to hear. As galaxies multiplied and stars ignited across the early universe, another structure was already in place, silent, unseen, yet decisive. Long before light revealed its patterns, dark matter had begun to shape the cosmic landscape. Dark matter does not glow. It does not absorb or emit light. It passes through ordinary matter without friction or resistance. And yet its gravitational influence outweighs everything we can see. Roughly 85% of all matter in the universe belongs to this invisible component, forming a vast framework upon which visible structures depend. Without dark matter, galaxies could not exist as stable systems. Stars at their outer edges would move too quickly, escaping into space. Clusters of galaxies would drift apart. The universe would remain a diffuse fog, never gathering into coherent forms. Dark matter provides the hidden mass needed to bind everything together. In the early universe, this framework emerged first. Slight variations in density, imperceptible differences left over from the Big Bang, allowed dark matter to begin clumping under gravity. These clumps grew into halos, massive regions where gravitational pull was just strong enough to draw in ordinary gas. Where dark matter gathered, visible matter followed. Over time, these halos connected to one another, forming elongated filaments that stretched across millions of light years. At the intersections of these filaments, matter accumulated more densely, giving rise to galaxies and clusters. Between them lay vast emptiness regions where little material remained. What makes this framework remarkable is its patience. Dark matter does not rush. It builds slowly, quietly, shaping the universe over billions of years without ever revealing itself directly. We detect it only through its effects, through the motion of stars, the bending of light, and the large-scale arrangement of galaxies. Recent observations have begun to trace this structure more clearly. Gravitational lensing reveals subtle distortions in the shapes of distant galaxies caused by unseen mass between them and us. These distortions map the presence of dark matter along filaments and nodes, confirming predictions made decades earlier. In this way, the universe resembles a vast invisible skeleton, with luminous matter draped delicately over it. Stars and galaxies are not free to form anywhere they choose. They emerge where the framework allows. And once this hidden architecture is in place, it invites a deeper question. If dark matter built the roads of the universe, how quickly did matter begin to travel along them? Among the many patterns revealed by deep observation, one stands out not for its brightness, but for its order. Astronomers call it the cosmic vine, a chain of galaxies aligned along a narrow path stretching more than 13 million light-years through space. At first glance, it resembles a coincidence. Galaxies are expected to cluster after all. But the vine is different. Its members are not loosely scattered. They are arranged with striking coherence, as if guided along a single thread of gravity. Nearly 20 galaxies appear bound within this elongated structure, all sharing a similar cosmic age. What makes this discovery unsettling is not its size alone, but its timing. The cosmic vine existed when the universe was only a few billion years old. According to conventional models, such extended and organized structures should require far more time to assemble. Gravity works patiently. Large-scale order is supposed to emerge late, yet here it is already woven. One interpretation is that the vine traces a particularly dense filament of dark matter, a region where the invisible framework was unusually efficient at channeling matter. Gas and galaxies may have streamed along this filament, like droplets sliding down a wire converging faster than expected. In this view, the vine is not an anomaly, but an extreme example of a process happening everywhere. Another detail deepens the mystery. The two largest galaxies within the vine appear unusually calm. Their star formation has slowed, even though galaxies of similar age elsewhere are still actively forming stars. This suggests that something intense may have occurred early on, perhaps mergers, or rapid bursts of star formation that exhausted their gas reserves. The cosmic vine feels less like a random gathering and more like a snapshot of structure mid-formation. A moment when gravity, dark matter, and time briefly aligned to produce order ahead of schedule. It invites a quiet shift in perspective. The early universe may not have been a chaotic scatter of isolated systems. It may have already known where it was going. Between solitary galaxies and massive clusters lies a quieter scale of structure galaxy groups. These are small communities of galaxies bound together by gravity, sharing a common environment as they drift through the cosmic web. They are neither isolated nor crowded, and in their slow evolution, they reveal how order gradually emerges from early chaos. In the young universe, galaxy groups were restless places. Their members showed irregular shapes, distorted arms, and intense bursts of star formation. Gas was abundant, collisions were frequent, and gravity had not yet settled into stable patterns. Everything appeared in motion, as if the structures themselves were still deciding what they would become. Observations now allow astronomers to follow these groups across billions of years. The change is subtle but unmistakable. Over time, chaotic systems grow calmer. Galaxies become more symmetrical. Star formation slows. Gas is heated, stripped, or consumed. What once looked turbulent begins to resemble order. This transformation is closely tied to dark matter. As dark matter halos merge and consolidate, their gravitational fields deepen. Galaxies are pulled into tighter orbits, interactions become more controlled, and the surrounding environment grows hotter and more stable. The group evolves from a loose association into a coherent system. Environmental effects play a crucial role. Within groups, galaxies experience forces they would never encounter alone. Hot plasma between them can strip away gas. Close encounters distort shapes and trigger brief but intense starbursts. Over time, these processes accelerate aging, turning active galaxies into quieter ones. What is remarkable is how early this evolution appears to begin. Even in the distant universe, some groups already show signs of maturity. This suggests that structure formation may have progressed faster than models once assumed, not only at the scale of individual galaxies, but across entire communities. Galaxy groups act as intermediaries, translating the invisible influence of dark matter into visible change. They are places where gravity teaches matter how to behave, and beyond these groups, where matter thins and connections stretch, the universe reveals a very different face. While galaxies gather along filaments and settle into groups, most of the universe does something very different. It empties. Between the glowing threads of the cosmic web lie enormous regions known as voids, vast expanses where matter is scarce, galaxies are rare, and darkness dominates. These voids are not small gaps. Some stretch hundreds of millions of light years across. Within them, matter density drops to a fraction of the cosmic average. If you could drift through one, the night sky would feel unusually quiet, with distant galaxies pushed far toward the horizon, leaving long stretches of apparent nothingness. Voids form through a simple but powerful process. Regions that began slightly less dense than their surroundings exerted weaker gravitational pull. Over time, matter flowed away from them, drawn toward denser filaments and clusters. As matter drained out, the voids grew larger and emptier, slowly inflating like cosmic bubbles. Because gravity is weak inside voids' motion, they're less complicated. Galaxies that do exist within them move almost entirely with the expansion of space itself. This makes voids valuable laboratories. They offer some of the clearest conditions for studying how the universe expands on the larger scales. Here, dark energy enters the picture. Dark energy is the force driving the accelerated expansion of the universe. Unlike matter, it does not dilute as space grows. Its density remains constant, meaning that as the universe expands, the total influence of dark energy increases. Over billions of years, it has come to dominate cosmic behavior. Voids respond strongly to this influence. As dark energy pushes space apart, voids expand faster than denser regions. Their boundaries stretch filaments thin, and galaxies slowly drift farther from one another. By measuring the size, shape, and distribution of voids, astronomers gain insight into how dark energy behaves over time. So far, observations show that voids largely match predictions made by standard cosmology. This agreement is reassuring but also intriguing. It suggests that while some parts of the cosmic story strain existing models, others still follow them closely. In the quiet interiors of voids, the universe reveals its most subtle motion. Space itself is not still. It is gently, persistently unfolding. And that unfolding leaves its mark not only on emptiness but on light. As the universe expands, it leaves a subtle signature on everything that travels through it. Light in particular carries this signature faithfully across immense distances. This effect is known as redshift, and it is one of the quiet keys to understanding cosmic history. When a distant galaxy emits light, that light begins its journey with a specific wavelength, determined by the atoms and processes that produced it. But as the light moves through expanding space, the space itself stretches. The wavelength of the photon stretches with it, becoming longer, lower in energy, and shifted toward the red end of the spectrum. The farther the light travels, the more pronounced this stretching becomes. Redshift is not caused by motion alone. It is not simply galaxies flying away through space. It is the expansion of space itself, gently pulling light apart as it passes. This distinction matters. It tells us that the universe is not expanding into something else. It is expanding everywhere, all at once. By measuring redshift, astronomers can determine how much the universe has grown since the light was emitted. A redshift of 1 means the universe has doubled in size. A redshift of 10 means it has expanded 11-fold. For the most distant galaxies observed by Webb redshift values exceed 14, revealing a universe that was once dramatically smaller and denser. Redshift also affects brightness. As wavelengths stretch, energy spreads out. Photons arrive more slowly and the light grows faint. This is why the earliest galaxies are so difficult to detect. They are not only distant, their light has been diluted by time itself. James Webb was designed with this challenge in mind. Its infrared instruments are tuned to detect light that has been shifted far beyond what human eyes can see. Where earlier telescopes saw darkness, Webb reveals structure, uncovering galaxies whose visible light was stretched into infrared long ago. In this way, redshift becomes more than a measurement. It becomes a translator between epochs. It allows us to reconstruct the size, temperature, and pace of the universe at different moments in its past. But as precise as these measurements are, they lead to a quiet tension. When scientists compare how fast the universe appears to be expanding at different distances, the numbers do not always agree. And it is within that disagreement that one of the deepest mysteries of modern cosmology begins to take shape. For decades, cosmology rested on a reassuring assumption. No matter how complex the universe appeared, its expansion rate could be measured, agreed upon, and fixed into a single number. That number would tell us how fast space itself is growing, how old the universe is, and how its future might unfold. But as measurements became more precise, something unexpected happened. The numbers began to disagree. One method looks deep into the past. By studying the cosmic microwave background, the faint afterglow left. When the universe was only 380,000 years old, scientists can infer how fast expansion should be today. This approach yields a slower rate, about 67 kilometers per second per megaparsec. Another method looks nearby. It measures distances to galaxies using well-understood objects like Cepheid variable stars and Type Ia supernovae. These cosmic markers act as distance beacons. When combined with redshift, they reveal how quickly nearby galaxies are moving away. This method consistently produces a higher value closer to 73. The difference may seem small, but it is persistent. Statistical noise cannot explain it. Independent teams, different instruments, and multiple analyses all point to the same split. This discrepancy is known as the Hubble tension. For a time, many hoped the issue lay in measurement error. Perhaps dust obscured stars. Perhaps telescopes blended light too roughly. The James Webb Space Telescope was expected to resolve this. With greater resolution and infrared clarity, Webb remeasured key distance markers with unprecedented precision. Instead of closing the gap, Webb confirmed it. The higher expansion rate held firm, the tension sharpened. This result carries a quiet weight. If both methods are correct, then something fundamental is missing from the standard picture of the universe. The laws describing cosmic expansion may be incomplete, Dark energy may not be constant. Unknown particles or forces may have influenced expansion early on, leaving an imprint that still echoes today. What makes this unsettling is its scope. The Hubble tension does not concern a single galaxy or a rare structure. It speaks to the universe as a whole. It challenges the framework used to interpret nearly all cosmological data. Yet even here, caution prevails. Scientists do not rush to rewrite physics lightly. They test, refine, and observe again. But with each confirmation, the question grows quieter and deeper. If the universe is expanding faster than we thought, then our map of cosmic history may be subtly distorted. And distortion once noticed cannot be unseen. For much of the 20th century, astronomers believed the observable universe contained roughly 200 billion galaxies. The number felt vast, almost beyond comprehension. It shaped our estimates of stars, planets, and the likelihood of life itself. Then James Webb looked deeper. In regions where earlier surveys saw only darkness or faint smudges, Webb revealed dense populations of galaxies, small, dim, and numerous. When scientists compared these deep fields to previous counts, a quiet revision emerged. The universe may not contain hundreds of billions of galaxies, but trillions. This change is not cosmetic. It alters scale. Each galaxy hosts billions, sometimes trillions of stars. Many of those stars form planetary systems. Even if only a small fraction of planets develop the right conditions for life, the sheer number of opportunities multiplies dramatically. What once seemed improbable begins to feel statistically inevitable. Yet this is not a statement about intelligent civilizations broadcasting signals across space. It is something softer, more patient. Life in its simplest forms may arise wherever chemistry has time to experiment. Given trillions of galaxies and unimaginable spans of time, experimentation becomes relentless. There is also a humbling symmetry here. The same cosmic processes that make life possible, stellar nucleosynthesis, planetary formation, stable environments, are woven into the large-scale structure of the universe itself. Life is not an exception to cosmic history. It is one of its expressions. But abundance does not guarantee connection. Cosmic expansion isolates regions of space from one another. Many galaxies will never exchange a single photon. Civilizations, if they exist, may rise and fall in complete silence, separated not by distance alone, but by the stretching of space itself. This reframes the question of life from one of contact to one of coexistence. Life may be common, yet forever unseen, present everywhere, yet unreachable. In this light, Earth becomes neither central nor insignificant. It is one instance among countless others embedded in a universe that is far more populated than we once believed. And as the number of galaxies grows, so too does the weight of the next question. If the universe is this full, this active, and this fast, why does our model struggle to keep up? There are moments in observation when familiarity breaks down. The data looks correct. The instruments behave as expected. And yet the result feels wrong, not because it is dramatic, but because it refuses to fit. This is where cosmology finds itself now. For decades, the laws governing gravity, motion, and expansion have worked remarkably well. They explain planetary orbits, stellar life cycles, galaxy rotation, and the large-scale structure of the universe with impressive accuracy. The standard model did not arise from belief, but from repeated success. But James Webb has begun to illuminate corners where that success grows uneasy. Galaxies appear earlier than they should. Structures form faster than predicted. Black holes grow too quickly. Expansion rates disagree depending on where and how we measure them. Each anomaly alone might be manageable. Together they create pressure. What makes this moment unusual is that the laws themselves have not failed locally. On small scales, gravity behaves as expected. In nearby galaxies, dark matter explains motion well. Laboratory physics remains untouched. The tension appears only when we stretch these laws across extreme distances and early times. This suggests something subtle. Not that physics is broken, but that it may be incomplete. Perhaps the early universe operated under conditions where familiar rules behaved differently. Perhaps additional components, fields, particles, or forms of energy played temporary roles and then faded. Or perhaps the assumptions used to extend local laws across cosmic history require revision. Scientists approach such possibilities carefully. Extraordinary claims demand extraordinary evidence. No single observation is enough to overturn a framework built over generations. Yet when multiple independent observations point in the same uneasy direction, they cannot be ignored. This is how physical revolutions begin, not with sudden collapse but with quiet accumulation, with results that whisper rather than shout, with a growing sense that the map no longer matches the territory. The universe is not defying physics out of chaos, it is inviting refinement. And as we move forward, the question becomes less confrontational and more reflective. Are the laws wrong, or are we only beginning to see where they bend? Much of modern cosmology is built on sequence. First matter cools, then it collapses, stars ignite, galaxies assemble slowly through mergers and gradual growth. Each step follows the last, guided by timescales set by physics. This orderly progression has long shaped how we imagine cosmic evolution. But some of the galaxies revealed by Webb seem to tell a different story. They appear as if several chapters were missing. Instead of small irregular systems still learning how to hold themselves together, Webb shows galaxies that already display compact cores, organized structures and concentrated stellar populations. Their light suggests maturity, not experimentation. Their shapes imply stability, not chaos. It is as if they arrived already formed. This impression challenges the idea that complexity must always emerge slowly. If these galaxies followed the expected path, there simply was not enough time. Gas needed to cool, halos needed to grow. Feedback from stars should have disrupted early assembly. Yet the evidence suggests these steps either happened faster or differently. One possibility is that conditions in the early universe allowed multiple processes to overlap. Cooling collapse and star formation may have proceeded simultaneously rather than sequentially. In denser environments, gravity could overwhelm, stabilizing forces compressing matter before it had time to resist. Another idea is that mergers were far more frequent than assumed. In a smaller universe, galaxies were closer together. Repeated collisions could rapidly build mass and structure, accelerating evolution in ways our simplified timelines do not fully capture. There is also the chance that what we interpret as maturity is deceptive. Bright, massive stars burn intensely but briefly. A galaxy dominated by such stars can appear evolved even if its total mass remains modest. Light, after all, does not always reflect age. None of these explanations stands alone. Each offers a partial glimpse into a process we are still trying to reconstruct. What remains consistent is the feeling that early cosmic development was not always patient or stepwise. The universe may have learned to build quickly when conditions allowed, and when development can leap forward rather than crawl, our timelines become guides, not guarantees. Among the most reliable tools in astronomy is motion. Light can deceive, brightness can mislead, but movement is harder to argue with. When stars orbit within a galaxy, their speeds reveal how much gravity is holding them in place. For decades, this principle has served as one of the strongest foundations of modern cosmology. It was through rotation curves that dark matter first made its presence known. In nearby galaxies, stars far from the center move too quickly to be bound by visible matter alone. Something unseen must provide additional gravity. Dark matter filled that role elegantly. The theory worked. It predicted motions accurately and consistently across countless systems. But when Webb began probing the earliest galaxies, that clarity softened. Some young galaxies show stars orbiting faster than their visible mass can explain yet, without the expected signature of massive dark matter halos. Others display the opposite behavior with rotation curves that decline too sharply, suggesting less dark matter than theory predicts for their age. These contradictions appear within the same epoch under similar cosmic conditions. This is not a small discrepancy. Rotation curves are not abstract measurements. If stars are moving at a given speed, the gravitational pull must match it. Otherwise, the galaxy should tear itself apart. The fact that these systems remain intact means something in our accounting is incomplete. Several interpretations are under careful consideration. Dark matter itself may behave differently in the early universe, forming halos with structures unlike those we see today. Alternatively, interactions between dark matter and ordinary matter may have been stronger in the past, altering how mass distributed itself within young galaxies. There is also a more delicate possibility. The laws governing gravity may subtly change under extreme conditions of density or scale. Such ideas are approached with caution, but they linger at the edge of discussion when familiar explanations strain. What makes this puzzle particularly unsettling is its timing. These galaxies are not ancient relics shaped by billions of years of interaction. They are young. Their motion reflects conditions close to cosmic birth. In their rotation, the universe seems to whisper that mass motion and gravity may not have always danced to the same rhythm, and if that rhythm once changed, it may echo through everything that followed. When motion refuses to match expectation, two paths quietly appear. Either something unseen is shaping that motion, or the rules describing motion need reconsideration. In cosmology, these paths lead to dark matter on one side and gravity itself on the other. Dark matter has long been the preferred answer. It explains why galaxies hold together, why clusters remain bound, and why large-scale structure forms the way it does. Its success is not theoretical elegance alone, but consistency across many observations. For most of the universe it works, yet the early galaxies observed by Webb introduce uncertainty. Their rotation patterns do not always align with how dark matter halos are expected to behave at such young ages. This has reopened a quieter question: could gravity itself act differently under certain cosmic conditions? Some alternative models suggest that at very low accelerations or extreme scales, gravity may subtly deviate from familiar laws. These ideas have struggled to explain the full range of observations, especially where dark matter performs well. Still, when motion resists explanation, they return to the conversation. It is possible that neither option stands alone. Dark matter may exist yet interact or distribute itself differently in the early universe. Gravity may remain intact yet operate within environments we do not fully understand. For now, this tension remains unresolved. It is not a crisis, but a reminder. When the universe moves in unexpected ways, it is inviting us to look again. For a long time, many believed the disagreement over the universe's expansion rate would quietly fade with better data. The expectation was simple: improve the measurements, and the numbers would converge. James Webb was built in part to do exactly that. Instead, it delivered a confirmation. With its higher resolution and infrared sensitivity, Webb re-examined the same distance markers used by earlier telescopes. Cepheid variable stars, long trusted as cosmic mileposts, were measured with greater clarity, less distortion from dust, and far less background interference. If the earlier results were flawed, Webb would have revealed it. It did not. The faster expansion rate remained. The gap between early universe predictions and local measurements held steady. What had once been dismissed as a technical problem became something more persistent. This confirmation shifts the meaning of the tension. It is no longer a dispute between instruments, but a disagreement between epochs. The universe, when measured close by, appears to be expanding differently than when its earliest light is used as a guide.